ahead and get to that. We are on approximately page 256. We're going to start a discussion on, 254, on atomic mass. Before we do that, let's go ahead and very quickly review yesterday. Yesterday we went over 3 basic types of reactions, and then on that third type we had a couple nuances, right? The first one, the most basic one, was what kind of reaction? Decomposition. We're taking a molecule and we're breaking it down into the constituent elemental forms. And for this class, it's always going to be a molecule that breaks it all the way down into pure elements, not breaking it down into other molecules and elements. Okay? So it's a decomposition. The second type, formation, the inverse of that, right? So we take the elemental forms, we combine them together in a reaction to produce the product, which is a molecule. And then the third type of reaction, combustion, which means, pardon?
Complete and incomplete.
Right. The basic type is combustion. We talk about 3 types of combustions, right? But just right now, when you think of combustion, what are you thinking? What's the primary description, or how is a combustion reaction described? What does it involve?
Oxygen.
No, right. I don't want you to think initially of burning. I want you to think initially of reacting with oxygen. That's the first thing. Reacting with oxygen. So a fuel of some type or a metal reacts with oxygen. Okay? It reacts with oxygen. Now, in the case of a metal, we have the combustion of metals. And when a metal combusts, it may burn in a traditional way. It may combine with oxygen using heat and produce, another form, but it may also look very different than that. It may be a rust. So basically what is happening is a metal is reacting with oxygen to form that metal's oxide. It's rusting. And so while you may think of the example I gave of the gearbox of the helicopter melting down and burning, it's also equally valid to think of a iron nail rusting. Those are both processes of oxidation. They're both taking the metal and combining it with oxygen, one through heat, using heat, and one using the ambient situation with no additional heat, but that both result in the metal oxide. That's the burning of metal, the combustion of metal, as a fiery experience and as a slow rusting experience. Those are both equally combustion of metal. Then we talked about 2 forms of combustion with a traditional fuel, a carbon-hydrogen, sometimes oxygen chain, that reacts with oxygen to form what 2 products? In a complete combustion, it's going to form what? You're going to have a fuel. You're going to have a fuel plus O2 produces carbon dioxide and water. So if you look at carbon dioxide and water, that is your, you've got all the components, the carbons, the hydrogens, the oxygens. They're going to take the carbon-hydrogen fuel, react it with the oxygen to produce carbon, hydrogen, and oxygen in the form of carbon dioxide and water vapor. Now that is a complete combustion because that means in the environment where the combustion has taken place, there's sufficient oxygen to produce carbon dioxide, CO2. Incomplete combustion is the case where there's insufficient oxygen in the space to allow that to happen. And because carbon monoxide and carbon dioxide, they're covalent molecules, right? They're legitimate alternate forms of carbon-oxygen combination. If the combustion process cannot produce CO2, it will produce, as an alternative, CO, carbon monoxide. Carbon dioxide is not healthy for you in large doses and is a greenhouse gas. Carbon monoxide will kill you. Okay? Again, I mentioned carbon dioxide will too in large concentrations, and just as water will, we call that drowning. Okay? But in moderation, carbon dioxide is not going to hurt you. You breathe it out all the time. You are an engine. Your body is an engine. You're taking in oxygen, and you're breathing out carbon dioxide. In your body, there's a burning process that's taking place, right? You're burning calories. The waste product of that burning of the calories in your body is carbon dioxide. That is what's formed when you breathe in the oxygen, and your body creates water and carbon dioxide. You go to a mirror, you breathe on it, it fogs up. Where did that water come from? The combustion in your body is producing the water. Okay? So you are the engine that's producing carbon dioxide and water in that case. So, decomposition, formation, combustion. Within combustion, we have combustion of metals in the form of a burning experience or a rusting experience, and we also have complete or incomplete combustion with a carbon-hydrogen fuel. There may be more to that, but that's the way to think of it, carbon-hydrogen fuel. Okay? But all the elements in the burn, or excuse me, in the combustion, will be accounted for in the product. So you're not going to lose any or gain any elements. So you should see every elemental symbol on both sides of the reaction. Okay, we kind of move away, the text kind of moves away from this idea of reactions and processes right now and gets into this idea of atomic mass. Now we've covered the concept of atomic mass, and forgive me if I restate some things that are obvious, but again, I've taught this course in several different orders, and it's hard for me sometimes to remember, is this the class where we did it this way or we did it that way? Could be a little bit different depending upon how it's taught. But this idea of atomic mass. So tell me real quickly, what do you remember about atomic mass? What is atomic mass? It's easily the mass of a given atom, an atom of a given element, right? What is the mass? Now, again, we tend to think in terms of weight. And when we talk weight and mass, I understand if you get those ideas mixed up, but an atomic weight is sometimes used, but that's not the same as atomic mass. What is the difference between weight and mass? And it's more of a physics question, but just so we make sure we understand it. Mass is a measure of what? A real untechnical term that I use in here.
Volume.
Not volume, no. Because density,
Not space.
not space, no. Mass is a measure of, okay, we'll use this in air quotes, stuffness. Mass is a measure of stuff. How much stuff, a real technical science term, right? Stuff. Mass is a measure of how much stuff you have. You can have the same amount of stuff in a space the size of this room or compressed to the head of a pin, but it's still the same amount of stuff. How much volume it takes up, that creates density, right? So mass is a measure of how much stuff you have. That's different than weight. Weight is what? Weight is not technically a measure of how much stuff you have. Weight is a measure of the force of gravity acting upon how much stuff you have. You're all familiar with this concept that if you weighed something here on the Earth and took that same item to the moon, it would weigh 1/6 as much. Okay? It would weigh 1/6 as much because the gravitational pull of the moon is 1/6 the gravitational pull of the Earth. That's why it would weigh less. But if it's the same stuff, you haven't lost anything, right? If I beam you to the moon, hopefully on the moon you would still be all of you. You know, more than 1/6 of you would show up. And yet if you stepped on a scale on the moon, your weight would be very different for the same amount of stuff. So I want you to keep that idea in mind as well. Mass is a measure of stuff, how much stuff. Weight is a measure of how much the planetary body you're on, or the celestial body you're on, how much it's pulling on that stuff to create this force, and that force is your weight. Again, that's more significant in physics. Yes?
So weight is relative.
Weight is relative to where you're located, right, your location. The gravitational pull of the location of where you're at. So the same amount of stuff in various places around the universe weighs very differently. Now, I also mentioned before we use the triple beam balance. The triple beam balance is a way that we measure mass, but it uses a process which uses the force of the Earth. So even though it's a triple beam balance and it's calibrated to measure the amount of stuff, it's calibrated according to the gravitational pull of the Earth. I could not take that triple beam balance in the moon, and it would not read the same thing. It would read 1/6 the mass. So we're actually measuring mass indirectly. We're using weight, and then based upon the gravitational pull of this planetary body, computing mass. if we took the triple beam balance of the moon, we'd have to accommodate it. We'd have to, cut the scale by 1/6, basically, because we account for the gravitational pull of the body. So, on the element periodic table, if you want to look at the front of your book or up here, if you can see this, we noted on here that most of the atomic masses in the book are rounded and to less precision than this one here. This one uses much more precision in their indications. But we have some basic numbers for every element. We've got the atomic number. The atomic number, for review, is the number of what? Potassium is 19. Atomic number 19. What does that mean about potassium?
That's the number of protons.
It's the number of protons and the number of electrons for the neutral atom, right? It's not an ion, which means the positives have to match the negatives. And for our purposes, we're considering the protons to be the positive. They must be balanced by an equal number of negatives, 19. The other number is the atomic mass. The atomic mass is an average. Remember we talked about isotopes? And how different isotopes of the same element can have different numbers of neutrons. But on the whole, on the average, this is a weighted average of the mass, meaning this is the weighted average of protons, neutrons, right? So protons and neutrons. So if I have the number of atomic number and I have the atomic mass, if I take the atomic mass, subtract the number of protons, I'm left with the number of neutrons. Now if you think of it that way, what is left out of the equation? What atomic particle do we know about that's not included in that consideration? Electrons, right. Where do electrons play? What role do they play in terms of determining the atomic mass? The way we've just described it, none. I want to offer to you that it's not that the electrons have no importance, but technically they do contribute to the mass of the atom, right? They're there. They're made up of stuff. And so electrons do impact how much stuff you have when you look at the individual atom. However, their mass is so insignificant compared to a proton or a neutron. They're so small. Say we have a bowling ball. We're trying to figure out the mass of the bowling ball. And somebody says, wait, let me drop a grain of sand in one of the finger holes. You know what? You may not even be able to tell the difference depending upon the precision of the instrument you have. But the mass of the electron is so incredibly small compared to the neutrons and the protons that practically speaking, it has no effect. It is there, it does contribute mass, but it has no real effect in terms of how we've calculated it. Now, we're going to introduce this idea of the atomic mass unit. You'll notice in your book on page 255, they give you an equation there, a definition actually, of 1 AMU. 1 AMU. AMU is an abbreviation for atomic mass unit. Atomic mass unit. Basically, it's a scale. If you think of it this way, it's an idea of scale to tell you how much. If I wanted to go and weigh an elephant, okay, would it make sense for me to bring you the measurement in ounces? I mean, I could. But the number's going to be huge, right? The number's going to be huge, and you're going to kind of lose perspective on it. I could give you the weight of an elephant in pounds, because that's what we typically think of weight as, pounds. I mean, I don't get on the scale and see how many ounces I weigh. I see how many pounds I weigh. And if I was a super big guy, maybe how many tons I weigh. But see, tons would be more appropriate for an elephant, right? How many tons does the elephant weigh? It's a scale that is in proportion to the thing being measured. And so tons make sense for an elephant. Ounces don't make sense. Could it be true? Yeah. Does it bring to you the sense of the scale and the size? Maybe not. Tons would do that. AMU kind of works in the other direction. An AMU is a unit of measure. It's a mass measure. And it's giving us the mass that's in proportion to or in scale to an individual atom. Incredibly small. Okay? So if I were to give you the mass of an atom in grams, it would be an incredibly small number. It'd be, in scientific notation, a number with a very large negative. As a matter of fact, it's 1.66 times 10 to the negative 24th grams. Can you wrap your head around the notion of 1.66 times 10 to the negative 24th? That's so incredibly small that, you know, if I said negative 24th or I said negative 25th, would you really pick up on a big difference? But it's 10 times difference, right? Negative 26 would be another 10th as big. So every decimal place is a 10th. We have a 10th of 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 a 10th. Keep counting it up. This is an incredibly small number if we're looking at grams. So in order to get it into a scale that we can actually do something with, that we can actually start to understand and place relative to one another, we use this unit called an AMU, atomic mass unit. And one atomic mass unit is the same as 1.66 times 10 to the negative 24th gram. So I've given you a statement of equality here, relating AMUs to grams. So what do you think we're going to be doing? We're going to be converting back and forth between AMUs and grams. Because I have a statement of equality, I can now produce a conversion factor. If I'm converting from grams to AMUs, I know that I'm going to have a 1 AMU over 1.66 times 10 to the negative 24th grams. So grams times that conversion factor is going to give me an answer in AMUs. Or the other way around, I can convert from AMUs to grams, grams to AMUs. And here's the deal. We can't, with any real degree of precision, measure out something according to the AMUs. But we can measure things out according to grams, right? If we can figure out a way to take the mass of an atom and convert it into grams, and then get it into the appropriate scale that we can use something like that triple beam balance over there, now we're getting to the possibility that we can actually count out how many atoms we have. We can say, for this many grams of something, we have this many individual atoms of that thing. It becomes important because, as we mentioned before, with balancing reaction equations, right? We have a reaction equation and we're trying to balance it. When I say that one of these and one of these produces one of these and one of these, the one of is atoms. The one of could be molecules, but it's 1 and 1 produces 1, or 1 and 1 produces 2, or whatever the coefficients of the balanced reaction equation indicate. And so what we're setting ourselves up here is the ability to transfer between AMUs and grams, and then to be able to take reaction equations and make proportional estimates. In other words, if I have 2 that produces a 1, if I have 2 atoms, it produces 1 molecule. If I have, and we're going to get into scale, which introduces us to the idea of the chemical mole. So, notice in the book, when we talk about an atom, in the book they give you this way of thinking about it. Did you have any idea that they were 1 trillion trillionths the mass of a housefly? 1 trillion trillionths the mass of a housefly.
How many zeros is that?
Negative, or 24 leading zeros. 24 leading zeros. Actually, 23 leading zeros and then 166. Okay. So that's how incredibly small it is. Example 7.4, we talked about using conversion factors. It says, figure out the mass of an atom, 1 nitrogen atom. That's what 7.4 asks. 1 nitrogen atom. What is the mass of 1 nitrogen atom? Well, we look over here, nitrogen, 14.0067 is the atomic mass on this chart. Your book probably runs it to 14. Most do. So if I know that one atom of nitrogen is 14, we're going to use 14.0 AMU. So what is the mass? What is the mass of one nitrogen atom? 14 AMU. Okay. What is that in grams? So you can see on 7.4, all we're going to do is create a unit conversion factor using this statement of equality. I need something that's going to change me from AMUs, and AMUs go in the denominator because I'm starting with AMUs and they need to cancel each other out. If it helps you, remember you can always put this, your given over 1 to make sure you keep the numerator and the denominator straight. So 14 AMUs times some conversion factor that's going to be grams over AMU, because the AMU is going to cancel AMUs and leave me with grams, and that's what I've been asked to solve for. So 14 AMUs times my conversion factor with grams over AMUs. Looking at my statement of equality, it's 1.66 times 10 to the negative 24th over 1.00. And then we just simply do the math. So 14 times 1.66, that's going to be 23.2. Yeah. So they 2.32, and then slide, because it's actually 23.2, we make the exponent 1 greater to negative 23. So times 10 to the negative 23. Okay. So that's all we're doing. We're using this conversion factor of 1 AMU is equal to 1.66 times 10 to the negative 24th grams. And now we can convert between grams and the mass of one atom of nitrogen. So if we had a device that was precise enough, and we were able to measure out nitrogen on the triple beam balance, and we were able to remove atoms of nitrogen off of the balance until we got down to 2.32 times 10 to the negative 23rd grams, we would know that we have one atom. Now, is anybody interested in the process of trying to take a sample of nitrogen and eliminate all but one atom? I mean, again, thinking in terms of scale, is that something that you think that we can functionally do? That it's doable for us to say, reduce the amount down to one atom? It's incredibly small, right? Incredibly small. What would be a way that we can measure out a known quantity, but maybe not settle for just one? Maybe not just say, I want one, but maybe let's say rather than having one of them, I want 10 of them, or 100 of them, or 1,000 of them. And you see, as I start getting larger and larger of the sample that I'm willing to measure out, we start getting into a range that we can actually begin to start doing stuff with. At some point, we're going to have so many atoms that it'll actually register on our triple beam balance. And we can add more and more and more and more stuff, more and more and more and more atoms, until we actually get to the place where we need to start adjusting the slides on the balance. We get so many trillions and trillions and trillions of atoms that we actually start to be able to measure it out, to figure out the mass of that huge sample. And that's what leads us into this idea of the chemical mole. Now, I could play videos and things like that for us today, because you can imagine having a unit of measure known as a mole is a source of a lot of comedy in chemistry. You know, everybody has these little images like gophers sticking their heads up out of the ground. They're not gophers, they got those weird faces, they look like rats, or like mice, not like, you know, a gopher would. But this idea of a chemical mole. And a mole, as I just said, is a unit of measure. In the same way that if I asked you, would you give me a couple marbles? You'd probably give me 2 marbles. If I said, give me several marbles, you'd give me 3, maybe 4 marbles. If I said, give me a dozen marbles, you'd respond by giving me 12. Now, what is dozen? Think about just the word dozen. We just know that dozen means 12, right? There's nothing about the word dozen itself that indicates 12 other than our recognition of that term, and we apply it. Say, Mr. Baker wants a dozen, I'll give him 12. Mr. Baker really wants a baker's dozen, it's just 13, right? Why I settle for just a simple dozen? I want a baker's dozen, it's one more. Or what about a score? When Abraham Lincoln said 4 score, what was he saying? 20 years each, right? So 4 score and 7 was 87 years ago. Just another way of saying how many, a score. If I said, give me, you know, and I'll stop at that. There's other words that we use that mean a certain number. They're units of counting. In chemistry, 6.02 times 10 to the 23rd is a standard unit of counting. When I say give me 1, you give me 1. When I say give me a couple, you give me 2. When I say give me a dozen, you give me 12. When I say give me a mole, you give me 6.02 times 10 to the 23rd of them. Okay? 6.02 times 10 to the 23rd. That's a huge number. In this case, as opposed to 1.66 times 10 to the negative 24th, which tells me that 1 AMU is an incredibly small number of grams, a incredibly small portion of a gram. On this unit of counting, in order to get enough of them to really do something with, I've got to have a very large count of them to be able to work with them. So that is 6.02 times 10 to the 23rd, known as Avogadro's number. Avogadro came up with the understanding that 6.02 times 10 to the 23rd of anything is the magical, no, it's not magical, but the mathematical, which sometimes is magic for us, right? Math is magic, okay? But it's the mathematical conversion between mass and individual piece count of something. Let's go ahead and jump right to using this. If you look at the figure 7.3 over on page 259, it shows different elements you've got and molecules. You've got molecules of water, sodium chloride, iron, and helium. And they suggest, by looking at that diagram, that you have gases, you've got liquids, you've got solids. So you've got all 3 phases. You have different masses, 18 grams, 58.5 grams, 55.8 grams, and 4 grams. They're all different masses. They're all different phases. But yet, in each one of them, they have 1 mole of atoms of that element or molecule, of that element or compound, in the form of atoms or molecules. Each one of those have the same count of how many molecules or atoms they have. Each one of them represents 1 mole of that compound or element. Each one of them has 6.02 times 10 to the 23rd individual pieces. So, with regard to atoms, that means individual atoms. So elements, it's individual atoms. For compounds, it's individual molecules. Because remember, we're not talking about how many pieces we have to build things with. We're talking about how many final structures we have. If I'm looking at an element, it's elemental form. For molecules, the complete mass of the the complete structure of the molecule. If I have 1 of them, for an atom, it might be 1 atom. But for water, it's 1 water molecule, because all I'm doing is counting them up. Imagine you're in the middle going 1, 2, 3, 4. And if you're picking up an element, you're picking up an atom. If you're picking up a molecule, you're picking up the whole structure. All you're doing is counting. 6.02 times 10 to the 23rd represents 1 mole count of whatever that thing is. But here's the trick. This is kind of cool. How do we get between AMUs and this count right here? See, because the magic of Avogadro's number is this. it's based upon how many of these do I need? How many of each given, right now we'll talk atoms, but I could just equally be talking about molecules, okay? But we'll just think about atoms for a minute. If I want to know how many atoms of potassium do I need to form a certain mass unit of that potassium? And here's the trick. If I look at potassium right now and I'm around this, it tells me here that the atomic mass of potassium is 39.0983. If I look in front of the textbook, potassium is just 39.1, okay? 39.1. So potassium has a mass, an atomic mass number of 39.1. Okay? Well, the way it's represented in the book here, you've got mass under, so I'll do it the way the book does it. Potassium 19 on top, atomic number 19, 39.1 is the mass. When I look at that element on the periodic table, 19 protons, 19 electrons, about 20 neutrons, an individual atom of potassium has a mass of 39.1 AMUs. 39.1 AMUs. Here is the essential correlation you need to remember. One atom of potassium is 39.1 AMUs. 1 mole of potassium is 39.1 grams. The same number, different units. So whereas potassium 39.1, potassium has a mass, and the mass of an atom of potassium is 39.1 AMU. The mass of 1 mole, also 6.02 times 10 to the 23rd atoms of potassium, has a mass of 39.1 grams. Okay? So looking at any element, let's go over here to sulfur, 32.1. Sulfur is 32.1 atomic mass. That means that one sulfur atom has a mass of 32.1 AMU. When you're looking at the individual, very, very small piece, 39.1 AMU. Is that what it said? 32.1. Sulfur is 32.1 AMU per atom. That's the mass of one atom. It's also 32.1 grams for 1 mole of sulfur. For 1 mole. So what this allows us to do is we can actually go over now to a triple beam balance. And if I have a sample of sulfur, and I pour sulfur on the triple beam balance, and I start taking the mass of it, if I were able to eliminate, slide off atoms of sulfur until my scale said I had 32.1, until I got down to 32.1 grams of sulfur, then I could say I now have 6.02 times 10 to the 23rd atoms of sulfur. And what does this matter for us in chemistry? Well, when we do a balanced reaction equation, remember when I said if we have, let me write something in front of the board for us to actually look at. If I said A plus 2B produces AB sub 2, and we went through this drill before, I said if one atom reacts with 2 atoms to produce 1 molecule, and 10 and 20 produce 10, and 100 plus 200 produce 100, because remember it's all in proportion. Now I get to the place where I say 6.02 times 10 to the 23rd plus 2 times 6.02 times 10 to the 23rd produce 6.02 times 10 to the 23rd. You see? The proportionality, 1 reacts with 2 to produce 1. Yes, sir?
Nitrogen produced.
So we've just taken this idea of 1 and 2 producing 1. If you remember when we did these before, I said, does anybody in here want to try to count out 1 atom of A and react it with 2 atoms of B to form 1 molecule of AB2? That's intimidating. But if I said, do you want to measure out 1 mole of A? Well, you can actually do that now, understanding Avogadro's number. If I want to measure out 1 mole of this, all I need to know is find out its atomic mass and measure out that many grams of it. And then I'll have 1 mole of it. And for B, I need to find out the atomic mass of B and measure out 2 times that atomic mass in grams to have 2 moles of this. And it will produce 6.02 times 10 to the 23rd molecules of the compound AB sub 2. Again, for you to go to the lab and try to measure out 1 atom and 2 atoms and then prove that it makes 1 molecule is not possible with the equipment and abilities we have today. However, you going in and measuring out 6.02 times 10 to the 23rd and 12.04 times 10 to the 23rd and proving that it produces 6.02 times 10 to the 23rd is doable. It's doable because we've now multiplied the reaction to so many times over that it actually becomes into our scale of visibility. We can actually see it, we can actually measure it, we can actually do something with it. We can use it to predict, and we can also use it to forecast. We can look forward and find out how much we're going to produce, and given how much we produced, we can look back and figure out how much we used up. Because we're now in the scale of something that we as human beings can actually work with by using the mole concept. So very important, top of page 259. It says there, the atomic mass in AMU will give the mass of 1 atom, and the atomic mass measured in grams will give the mass of 1 mole. 1 mole being 6.02 times 10 to the 23rd of whatever structure we're looking at. That's why it shows it there, both the atom and the molecule applies both ways. Now, what is the mass of a molecule? If I look at this reaction equation here, it says A plus 2B produces AB2. If I know the mass of A, and I know the mass of B, what is the mass of AB2? Well, it's just simply the sum of the masses, isn't it? What is the mass of an AB2 molecule? Well, it's 1 times the mass of an A atom plus 2 times the mass of a B atom. So this is a conservation of mass kind of a thing. The mass of a molecule is equal to the sum of the masses of the elements that make up that molecule. If I do a formation reaction, and I look at the mass of each element that forms that molecule, and consider how many of each I need, and I add those masses together, I end up with the mass of the molecule that's created. So in terms of AMUs, the mass of AB2 is the equivalent of the number of AMUs of A and 2 times the number of AMUs of B. Add those together and that'll be the mass of 1 AB sub 2. Or, in terms of grams, the mass of 6.02 times 10 to the 23rd atoms of A plus 2 times the mass of 1 mole of B gives us the mass of 1 mole of the molecule. This is a conceptual thing, but it's just a matter of scale. The mass of 1 plus 2 times the mass of the second produces the mass of the molecule. Again, I'm using this because the implied coefficient of 1, the given coefficient of 2, and the implied coefficient of 1. Let's go ahead and consider example 7.6 in our close for today. 7.6 says, how many moles of fluorine atoms exist in a 50-gram sample of fluorine? How many moles exist in a sample of? So, we're given, we have a 50-gram sample. We have 50 grams of fluorine, right? And the question is, how many moles of fluorine is that? Well, I have a sample of grams, and I need some kind of conversion factor that's going to take me to moles. Right? I have 50 grams, 50.0 grams. I'll put that over 1. So 50.0 grams of fluorine. And I'm looking at my end result. I'm looking for moles. So my conversion factor, where does moles go? The numerator or the denominator? The numerator. Good. So moles. Now what am I trying to get rid of on this side of the equation? Grams. So I need grams in the denominator. I need to ask myself, do I have some relationship between moles and grams?
Yep.
Okay?
Then it's a 6.02 times 6.23.
No, that's a count, how many pieces per mole. But we do have a periodic table, right? And we're told what element are we looking at? Fluorine. So let's go over to fluorine. And the atomic mass of fluorine on here is 18.998. Basically 19, right? By that I know that 1 mole of fluorine has a mass of 19 grams. Because I looked at the periodic table. So if I have 19 grams of fluorine, I have 1 mole of fluorine. Let's bring it back and make that our conversion factor. 1 mole of fluorine is equal to 19.0 grams of fluorine. That's my conversion factor. So grams cancels grams and leaves me with moles. So the math comes out to be 2.63. 2.63 moles of fluorine is in 50 grams of fluorine represents 2.63 moles of fluorine. What does that mean? If I say, okay, you've got 2.63 moles of fluorine, how many atoms of fluorine do you have? Well, then you take 2.63 moles, and I've asked you for how many atoms. I'm trying to get rid of moles to give me how many atoms, right? And we know that 1 mole is 6.02 times 10 to the 23rd atoms. So in this case, I would do the math, multiplying 2.63 moles times 6.02 times 10 to the 23rd atoms per mole, and that would tell me how many atoms I have altogether. So by knowing the mass and knowing the element, you can compute how many moles that is, which is another way of saying how many atoms you have. Moles is a scale for the measure of pieces. In the same way, if I said I had so many grams of H2O, okay? Let's say we had 50 grams of water, and I wanted to say how many moles of water do I have? I would go through and I would add up 2 times the mass of hydrogen plus 1 times the mass of oxygen, because that's going to be the mass of my H2O molecule. And the mass of the H2O molecule, 18, because oxygen's about 16, oxygen's 16, hydrogen's 1, so the mass of a molecule of oxygen, or excuse me, mass of water is 18 grams per mole. 18 grams per mole would go in here, rather than 19, it'd be 1 to 18, and I would have a slightly larger number of the moles of water if I had 50 grams. Because each atom has a slightly smaller mass. That's 1 AMU smaller mass than fluorine. Okay?